Hi, we are group number 70 and we will be presenting paper number 2, Déjà Vu, Continual Model Generalisation for Unseen Domains.
AI works great when it's in its comfort zone, but what happens when it encounters something new? This unfamiliar period is where many AI systems falter, whether it's a phone camera failing to adapt to sudden light changes or an algorithm trying to recognize an unseen object.
Imagine a self-driving car struggling to navigate a sudden fog bank, or a security camera going blank during a snowstorm. These unfamiliar periods can have serious real-world consequences. While methods like domain adaptation and domain generalization exist, they are often too slow or suffer from catastrophic forgetting, where they lose knowledge of older data.
Basically, this paper talks about a new way to turbocharge AI learning. To achieve this, the authors propose RATP, a framework with three main objectives.
1. Target Domain Generalization (TGG), which improves performance on unseen domains. Second, Target Domain Adaptation (TDA), which provides better adaptation through top 2 pseudo-learning, which we will come to. 3. Forgetting Elevation (FA), which retains performance on older domains via prototype contrastive alignment, which aligns domain representations.
Let's try and simplify the problem statement first. This paper attempts to solve continual domain shift learning, or CDSL, where a model is trained on a labeled source domain and must adapt to unlabeled target domains appearing sequentially. In CDSL, we start with a labeled source domain dataset. Following this, a sequence of unlabeled target domains arrive continually. Each target domain contains inputs without labels, and all domains share the same label space as the source domain.
In CDSL, we have to keep in mind the constraints of memory and privacy as well. To address this, a small memory stores a few samples from previous domains, chosen for the similarity to class centroids, helping the model learn effectively. The memory is much smaller than the dataset, ensuring both efficiency and privacy. The model used is a deep neural network with two parts, a feature extractor and a classifier. For each new target domain, the model builds on the version from the previous domain. Let's start with random mix-up.
That sounds a little counterintuitive to what we want to achieve.
Yes, but we use randomness to augment our dataset. Imagine teaching AI about cats by sending information about cats, along with some of other pictures of dogs or just random textures. Intuitively, you might think this would confuse the AI, but rather it ensures that the model learns more adaptable features and makes it less reliant on specific details. So instead of just memorizing every cat picture ever, the model learns the underlying concept of catness. This figure depicts how ranmix works. As you can see, we inject noise at various stages to add to the randomness.
This slide just shows mathematically what we described in the previous slide. We use an autoencoder and inject noise into it by using add-in. We further introduce randomness by mixing the outputs with random weights.
Moving on to T2PL, or top 2 pseudo-learning. T2PL works by selecting and using only the most confident samples for labeling. After calculating the confidence for all samples, T2PL selects the top 50% of samples and creates the centroids for each class by averaging their features, weighted by their confidence scores.
Next, the cosine similarity between the centroids and all unlabeled samples is computed. T2PL then selects the top half samples that have the highest similarity to their respective class centroids. T2PL uses a K-NN classifier because it reduces the risk of errors caused by directly comparing samples to centroids and is better at handling highly overlapping classes because it looks at local neighborhood information.
For the final pseudo-labeling step, T2PL narrows down the selection to only the top 5% of samples for each class, ensuring only the most confident and accurate labels are assigned.
Moving on to another key component of the model, prototype contrastive alignment. Firstly, we use domain alignment to make sure that models trained on one dataset or domain can work well on another dataset with different characteristics. We also introduce contrastive comparison as part of this alignment. To draw an analogy of what contrastive comparison is, imagine you're training a child to group similar toys, example cars, dolls, and separate different ones. If you show to them two cars, they should say, these are similar. If you show them a car and a doll, they should say, these are different. Similarly, the goal is to teach the model to assign closeness to similar things and distance to different things.
Knowledge distillation ensures the new model retains knowledge from the old model, preventing catastrophic forgetting that we mentioned early on during domain adaptation. As you can see, this is how the loss function ends up looking like. It's the scary looking math equation, but luckily we don't have to solve it ourselves. Since D1 is the first data set, there is no prior data, and hence there is no distillation loss to solve for.
Let's now walk through the datasets, experiment settings, and comparison baselines used in the experiments. As we shall show in the next slide, the model beats current state-of-the-art methods by 3 to 10%. RATP does especially well in the field of domain adaptation. In all cases, RATP is the best, or at least very close to it. The authors also performed ablation studies on RANDMix, T2PL, and PCA, which showed that each component plays a crucial role in making RATP the best performing model.
This study compares RATP with existing methods across 3 different metrics: TDG, TDA, and FA, as we mentioned early on in the first slide. Results show that RATP outperforms baselines, especially in TDG, with up to a 10.3% improvement. It also demonstrates strong performance in TDA and FA, helping mitigate catastrophic forgetting and improving domain adaptation. These results highlight RATP as a promising method for domain adaptation tasks.